Okay, let's talk about gas transport and information from this specific area. There will be probably proportionally more questions about this than the other areas, even though it's all important. All right, so what we want to do is talk about how is oxygen transported in the blood, because there's two major ways that oxygen actually is carried in the blood, and then carbon dioxide, there's really three ways it's carried in the blood. And understanding that actually opens up some other areas of understanding that we'll talk about, and then understands the variables of the partial pressure of oxygen and the partial pressure of carbon dioxide, and especially the partial pressure of oxygen. We're going to start out kind of talking about that. Well, we know the partial pressure of oxygen in an alveolus is about 104 millimeters of mercury. The partial pressure of the oxygen on the returning blood supply is only 40, so we know it's going to go from the high to the low, and that was our partial pressure gradients that we've talked about previously. But what we want to concentrate on this lesson is, where does oxygen go once it goes into the bloodstream? We know that the majority of it is going to actually go and attach to a red blood cell, attached to the hemoglobin, specifically the iron on the heme groups in the hemoglobin, and then a small percentage of it will just diffuse directly and stay in the plasma of the blood. So as a matter of fact, percentage-wise, we see that 98.5%, so by far the greatest amount of oxygen, is actually going to bind to the hemoglobin in our red blood cells, and only 1.5% will then just dissolve in the plasma. Okay, let's see if we can interpret what's going on in an oxygen hemoglobin dissociation curve. So for instance, in this oxygen hemoglobin dissociation curve, notice what we've got. We've got an axis that talks about the percentage saturation of hemoglobin. In other words, if you were fully saturated, it'd be at 100%. And then we have the partial pressure, which we know the partial pressure in the alveolus is 104. But let's say in a typical resting cell, the partial pressure may only be 40. And so therefore, or in the blood, for instance, I should say, in the blood, the partial pressure also was just 40. So when we look at this graph here, what we're saying is that this graph is kind of an S-shaped curve. So we're saying that notice, like I said, we're never 100% saturated, but if we're right at this point right here, where the partial pressure of oxygen is above 100, then it looks like we can get to almost 100%. So we can get to almost about 98% saturation if my partial pressure is above 100. So notice, here's my partial pressure, and it goes a little bit above 100 here. And then, so how much of my red blood cell would be saturated? Well, about 98%. So that means it might hold about 980 million molecules of oxygen. Well, what if it were 80%? What if my partial pressure was 80 millimeters of mercury? Then what would my percentage of saturation be? Well, I would follow this up until it bisects the line here, and I'll look at that and I go straight across, and I say, well, that's still pretty high, because I'd say 90 is right here, so I'm still above 90, so I can still be fairly saturated even if my pressure drops. But notice here the curve has a steep drop to it. So if my partial pressure was 40, then notice then my saturation rate drops to about 75. And if my saturation was 20, it drops all the way to probably the low 30 saturation. Now, what that actually means is that when the blood is in the lungs, it's going to be we're going to have high partial pressure of oxygen. Therefore, the blood is going to become highly saturated. But when the blood moves to areas of the body that has low partial pressures of oxygen, then that means the blood is going to start giving up that oxygen, and then its saturation rate is going to drop quite a bit. So we know the lungs have a high partial pressure of oxygen in them, about 104. Therefore, the blood, once it goes to the lungs, has a very high saturation. In other words, how much oxygen is binding to that hemoglobin.
Pressure of oxygen is approximately 100 millimeters of mercury.
How much? So it can be 100 or up to 104 in the lungs. Now, that would be if we were at sea level. Remember, though, if we were actually at a higher elevation, then our partial pressure of oxygen would be less because there's less oxygen molecules. So it may drop a little bit, but that wouldn't change the fact that we're still in this curve, we're still at a very high saturation rate. In other words, how much of that oxygen is being held onto that hemoglobin. Okay, now, well, other places in the body is not going to have as high a partial pressure of oxygen in them, primarily because the other parts of the body are not receiving oxygen, they're using up oxygen. So when the blood flows past those areas that actually have a lower percentage of hemoglobin, then it's going to start giving up that oxygen, and its saturation rate is going to be small, is actually going to lessen. So again, here, my lungs had, 100 to 104, and then if my elevation dropped a little bit, maybe my partial pressure dropped a little bit, but my saturation was still high. In other parts of my body, my partial pressure of oxygen is lower. Let's say I'm at an area where it's 40. Now, because I'm going to start giving up oxygen at that area, my percentage of hemoglobin saturation is less. So I'm down to 75 here, where I was saturated to 98 to 95% up here. So for most of the body then, when the blood is circulating here into the alveoli, and we're getting a large partial pressure of oxygen in the lungs, then the blood is going to be anywhere from 98 to 95% saturated. But as the blood circulates down here to the tissues, where their partial pressure is around 40, then we have to start giving up that oxygen. Therefore, our saturation rate drops wherever we give it up. Now, if we have tissues that even have a lesser partial pressure of oxygen because they're literally using more oxygen, then we start giving up even more oxygen, and our saturation rate keeps dropping. So again, we see this S-shaped curve, and we see that the flat slope is, so this is pretty flat up through here, especially right here where we would be in situations where we're receiving a fairly high partial pressure of oxygen in our lungs. Even if whether we're at sea level or we're at higher elevations, we still get a high saturation rate. At our steep slope, though, notice how steep this is, then we're going to have our low. Notice our low. Notice that this drops much quicker between 40 and 20 than it did between 100 and 80, even though it's still just 20 millimeters of mercury either way. We didn't lose much saturation here, but we lost a lot of saturation for going from this point to that point. Okay, now again, we said the blood, when it goes back, from the right side of the heart back into the pulmonary trunk and pulmonary arteries, and then to the capillaries that are surrounding the alveoli. Remember, we said we're never oxygenless, we're just oxygen poor. And when we say that, we're saying, well, that's how saturated. They still have some oxygen, even if we were down to an extremely low partial pressure of oxygen, then we would still at least be 30%. Our saturation rate would still be 30%. But most of the time, we're around 75% is one of the lower that actually are lower saturation rates in our body. So most of that blood that's even circulating back is still 75% saturated, but we go from 75 to 98% saturated for most blood cells once we get back here at the capillaries around the alveoli. And again, here we see the difference between somebody at sea level versus somebody way up in elevation. Again, in the lungs, where you're taking all that oxygen in, you're going to have a high level of a high pressure, partial pressure of oxygen, and so your blood, again, your hemoglobin and your red blood cells would only drop from 98 to 95%. So you're still going to be very saturated even if the partial pressure drops. but in your tissues away from your lungs, then the drop is going to be more drastic. Now notice as blood circulates through the body, then the partial pressure in the tissues, not in the lungs now, but in the tissues, in resting tissues, the partial pressure is only 40, so when blood goes by it, it's going to start giving off some of the oxygen, and it's going to drop its saturation. It went from having a lot of oxygen in the lungs to now we're at the tissues. They need the oxygen, so the blood gives off the oxygen, so now we're 75% saturated. Well, what about very active tissues like muscles? Like when you're working out and you need more oxygen, then they're using it up so much that the partial pressure of oxygen drops as it uses it up. So when the blood circulates past the muscles that are using up, so it's got a very low partial pressure, then we have to even give up more oxygen. Therefore, the blood goes all the way down to being about 35% saturated. So that blood, again, it never gives up all the oxygen, but it's very low saturation. So that has to circulate back to the lungs, pick up that high partial pressure of oxygen at the lungs, and be able to keep circulating through the body. Okay, besides the hemoglobin, besides the partial pressure dropping and our blood having to give up more, these are other factors that also affect the saturation rate. One is pH, temperature, carbon dioxide, and the production of a product called BPG. Now, let's talk about these three, because think about it. When you're exercising, obviously if you're exercising, your saturation rate is going to fall because you have a lower partial pressure because you're using up so much oxygen. Okay, so what happens to your pH when you exercise? Well, you form lactic acid, so your pH actually drops, because remember, low pHs is acidic. What happens to your body temperature when you exercise? Well, it rises. What happens to your carbon dioxide production when you exercise? Well, you produce more of it. And finally, you also produce more BPG. Now, again, notice your pH drops. Why? Because acid has a low pH. You're producing lactic acid when you exercise. Okay, temperature increases because you're using the muscles, burning that energy. Your carbon dioxide levels increase because you're burning up more glucose, therefore you're producing more carbon dioxide. And then a byproduct of this process is BPG, so that also increases. So if that's the case, then what would happen if you quit exercising? You have relaxed tissues. Then what's going to happen then? Your pH is going to rise, your temperature is going to fall, your carbon dioxide levels are going to fall, and your BPG is going to fall. That's actually going to do the opposite effects of exercise. Well, those four factors actually cause the curve to shift to the right. Now, if we look at this, here was our normal curve, our normal line. Again, this is what we looked at before. And again, as our partial pressures fell, then the curve did this steep drop through here. But if our pH lowers, our carbon dioxide raises, our temperature raises, and we increase our BPG output, then what's going to happen here is this curve shifts to the right even more. So looking at this, notice as our pH fell, okay, if our pH falls in addition to our partial pressure of oxygen being lessened, notice that the curve goes more to the right. So let's look at an example. If it were only, the lowering of the partial pressure of oxygen, then our blood would have been about 35% saturated at this point. But if we do that plus our pH dropping while we're exercising, producing that lactic acid, then notice that our curve shifts to the right. So now if we bisect, where that partial pressure and the curve is because of this extra force that's shifting it to the right. Now, instead of being 35% saturated, we had to give up even more oxygen, so now we're only 25% saturated. Okay, and so again, if our pH dropped because we're forming lactic acid, then we gave up more oxygen, and that also applies to these others. If our body temperature rises, then the shift goes to the right. If we produce more carbon dioxide, the shift goes to the right, produce more BPG. But the opposite occurs. Say my body temperature lowers, then instead of the curve shifting to the right, the curve would actually shift to the left. If I'm not producing as much carbon dioxide, then the shift goes to the left. So here we see he's quit